Hello everyone, today I will introduce our work ZnG, which is architecting GPU with new flash for scalable data analysis. Traditional computer systems usually employ GPU and storage as discrete devices to process larger scale data-intensive applications. The application's dataset usually initially reside in the SSD but should be processed in the GPU. Transferring the data from the SSD to the GPU need to go through multiple software layers and hardware boundaries. This step becomes the performance bottleneck. We break down the total execution time of the evaluated workloads into storage access time, data transfer time, and GPU processing time. As you can see from the right figure, the average data transfer time accounts for 71% of total execution time in our evaluated workloads. To eliminate the data movement overhead, prior work proposed hybrid GPU. It replaced the GPU side memory with a ZSSD. GPU can directly access the SSD through the customized interface. With the hybrid GPU design, the GPU can leverage the high storage capacity to accommodate all the dataset. It can reduce the power consumed by the DRAM. It also eliminates the redundant data copy. However, there is a huge performance disparity between the GPU and the ZSSD. For example, the GPU cores can deliver tens of teraflops throughput, while the SSD can only serve a few gigabyte data in 1 second. We analyze the performance of each component within the ZSSD. As you can see from the right figure, the request dispatcher, DRAM buffer, flash channel, and FTL cannot match with the bandwidth of ZNAND read operation. We designed a new GPU SSD architecture to deliver high throughput of ZNAND to the GPU. We call it ZnG. We replace the traditional flash channel with a high-performance flash network. The new flash network is built from the mesh network, which enables the flash controller to access any ZNAND package. Since the DRAM buffer performs much worse than ZNAND, we detach the DRAM buffer from the SSD data path. Instead, we make the GPU directly access data from ZNAND. We also need to remove the performance bottleneck, which is caused by the GPU network interface and FTL. In our design, the SSD controller is detached from SSD. We directly attach the flash controller to the GPU network, as the L2 cache bank can communicate with any of the flash controller. This design can improve the network parallelism. We integrate the request dispatcher in each flash controller to interact with the GPU network. We also leverage the existing GPU hardware to accelerate the FTL and achieve zero overhead. We split the functions of FTL into 3 parts. A block mapping table is integrated into the MMU to serve the read request. A read mapping table is integrated into a ZNAND internal row decoder to serve the write request. We also create a helper thread for the flash block merging, garbage collection, and wire leveling. To maximize the flash bandwidth, we leverage the GPU L2 cache to buffer the flash pages for the small reader and the read request. We increase the GPU L2 cache capacity by employing the STT run. We further improve the cache utilization by designing a dynamic prefetch scheme. It includes 2 new hardware. A prediction table examines the read request and decides whether to perform data prefetch. An access monitor dynamically adjusts the best prefetch granularity. We leverage the flash internal register to buffer and merge small write requests. We increase the number of flash registers in each flash die. We design a shared data path between the ZNAND array and any flash register to enable direct communication between each other. To maximize the flash register utilization, we group the flash register across all ZNAND arrays within the same die to serve as a fully associative cache. In this design, data can be placed in anywhere within the flash register. To achieve this, we employ a simple interconnection network within the ZNAND die. We compare the ZNAND access bandwidth of different system configurations. As you can see from the figure, hybrid GPU only achieve 4.2 GB per second. This is because of the limited flash channel bandwidth and FTL performance. In contrast, ZnG fully redesigned the hardware component in the SSD. That can be the performance bottleneck. It also optimizes both read and write bandwidth, so ZnG can achieve the best performance.